Hi everybody. I've put together a series of videos to help you with right-angled triangles. This includes the Pythagorean theorem, sine, cosine, and tangent when you're solving for a side and when you're solving for an angle. I have every algebraic permutation that's possible for a single triangle. I've combined them all into 11 short videos, which I will share as a single video as well. I hope you find it useful. Please share with your friends, and thank you for watching.
We have a right-angled triangle and no angles are involved. The approach would be to use the Pythagorean theorem. So we have x squared equals these quantities. Now how do you arrange the equation? Maybe you've said a, b, and c in the past. What I like to do is just say that the longest side goes by itself, which in this case is the quantity x. X is not by itself because it's a variable. It is simply the longest side, or the hypotenuse. We can simplify the right-hand side by evaluating the squares, simplifying to x squared equals 29, and then we take the square root of both sides, giving us an exact answer of root 29 centimeters, or to one decimal place, 5.4 centimeters. Here we have the second situation for the Pythagorean theorem. In this case, we're solving for a side and no angles are involved. This is also like the previous example where we use the Pythagorean theorem. In this case though, notice that the 13.1 is on its own. This is because, remember, the longest side goes by itself. We don't put the x by itself because it's a variable and the variable is special. We always put the longest side by itself, which in this case is 13.1 centimeters. Let's evaluate those exponents as follows, and we'll move the 67.24 to the other side, simplify, subtract, take the square root, and to one decimal place, the answer is 10.2 centimeters. We have a right-angled triangle in which we are solving for a side, and one of the other angles is given. Let's label the triangle, and notice that I've highlighted the opposite and the hypotenuse as being either given or what we want to find. The most appropriate ratio to use is therefore sine, since sine, in this case of 42 degrees, is opposite over hypotenuse. Let's put those quantities in the fraction. In this case, the variable is in the numerator. When the variable is in the numerator, you multiply. Simplifying this, we get 26.5 meters. We have a right-angled triangle in which another angle is given and we want to solve for a side. Let's label the triangle using the 70-degree angle as a reference. Notice that I've highlighted the opposite and the hypotenuse, like the previous example, so in this case, we would use the sine of 70 degrees, since sine is opposite over hypotenuse. Let's put the quantities in. In this case, the variable is in the denominator. In contrast to the previous example, we would divide here 3 by sine 70 degrees. Using the calculator, we obtain an answer of 3.2 feet, rounded to one decimal place. We have a right-angled triangle in which an additional angle is given, and we want to solve for a side. In this case, let's label the triangle relative to the given angle of 30 degrees. Notice I've highlighted the x and 15 centimeters as the adjacent and the hypotenuse in red. We should use the cosine ratio because we want to find x and we need to use the 15 centimeters given in the question. Cosine is defined as the adjacent over the hypotenuse, which in this case is x over 15. In this case, since the variable is in the numerator, we should multiply the two quantities. We practiced this with sine a couple of examples ago, and using the calculator, we can round the answer to one decimal place. We have a right-angled triangle with an additional angle given, and we would like to solve for a side, in this case, x. Let's label the triangle and determine which ratio is most appropriate. Notice that I've highlighted the x and the 16.6 centimeters as the hypotenuse and the adjacent. This means that we should use cosine, since cosine is defined as adjacent over hypotenuse. Substituting the information, we get 16.6 over x. In this case, and in contrast to the previous example, the variable appears in the denominator. Therefore, we can rearrange and divide by cos. So when the variable's in the numerator, you multiply, and when the variable's in the denominator, you divide. We can evaluate this to one decimal place using the calculator, giving us an answer of 19.4 centimeters. Here we have a right angle triangle with the additional 38-degree angle given. Let's label the triangle and determine which ratio is most appropriate. Notice I've highlighted the opposite and the adjacent, which are x and 19.5 feet. The tangent ratio is most appropriate in this case, and when written as opposite over adjacent, with the quantities given, that'd be x over 19.5. With the variable in the numerator, we multiply to obtain the final result, which is 15.2 feet. We have a right angle triangle in which the 64-degree angle is also given. Let's label this triangle to determine which ratio is most appropriate. Notice that I've highlighted in this case the opposite and the adjacent. Therefore, we should use the tan ratio. Let's write down the tan ratio, and the tan of 64 in this case would be the opposite, which is 5, over the adjacent, which is x. In contrast to the previous example, the variable appears in the denominator. In this case, we divide the 5 by the tan ratio, and with the calculator, we obtain an answer to one decimal place of 2.4 meters. Here's the first example in which we're going to solve for an angle. In this case, let's just label the triangle and see what happens. We have the hypotenuse, which is always opposite the right angle. The 5 meters is opposite to the desired angle theta, and then the other side labeled as adjacent is something that we really don't need to have or find. Using the SOHCAHTOA acronym, we can see that sine is the most appropriate ratio to use since we have the opposite and the hypotenuse. Let's write down sine of theta. Using that fraction, we would have 5 over 17. In contrast to the previous examples, we are now solving for an angle. So what do? You take the inverse. Let's do that as follows. Notice that I don't really care what 5 over 17 is as a decimal. I just can do that on my calculator with brackets or with a couple of operations. So don't waste your time making that into a decimal if you don't feel like you want to write that down. And when you evaluate the inverse, you get 17.1 degrees. We'd like to solve this right angle triangle for the angle theta. Let's start by labeling the sides. First, beginning with the hypotenuse, which is always opposite the right angle. I'll label the opposite side to theta. Notice that I've put it in gray here because I don't really need it and I don't want to find it either. Then we also have the 6 feet, which is the adjacent. Writing down SOHCAHTOA, we can decide here that cosine is the most appropriate ratio to use since we have the adjacent and the hypotenuse. Cos of theta is therefore equal to the adjacent 6 over the hypotenuse 9, 6 over 9. Since we're solving for an angle, remember that you need to take the inverse. So theta is going to be the inverse of that. Now 6 over 9, you could write that as a decimal, or you can just use brackets with your calculator. So you could evaluate 6 over 9 first, or just do this in one step. I do this in one step on my calculator, and it gives an answer of 48.2 degrees. Here's the final of 11 examples getting you from the Pythagorean theorem to sine, cosine, tan, and inverse sine, cosine, and tan. Let's go. Okay, so in this case, we'd like to solve for an angle when given a right angle triangle and two sides as follows. Let's label the triangle and see what happens. So the hypotenuse here is opposite the right angle. Notice I labeled it in gray because I don't really want to find it and I don't care what the value is for that. The opposite is 3, and the adjacent in this case is 2 centimeters. Okay. Writing down SOHCAHTOA, we see that the most appropriate ratio to use is opposite over adjacent, which is tan. So let's write tan of theta and put the quantities. So we would have tan theta is equal to 3 over 2. We'd like to solve for an angle. So in this case, we take the inverse. That is, theta is equal to tan inverse of 3 over 2. Or if you want tan inverse of 1.5, using the calculator, I get an answer of 56.3 degrees.